start by that. Any question? No? Okay. I'll start with a few remarks. Okay. So let me remind you that we defined this morning a planar map. Okay. All the map we will consider are planar. So a map is an embedding of a planar connected graph into the two-dimensional sphere S2, but you can deform your embedding by a continuous and orientation-preserving deformation, and the object that the two objects that we obtain are considered as the same map. Okay, so let me first put the emphasis on the fact that with this definition, it's not clear a priori at all that there is only a finite number of maps with a given number of edges. Okay, well, because an embedding, you've lot of embeddings, and then your deformations, you can imagine silly things, the monsters. So it's not clear at all that you can extract a combinatorial object from this definition. But it is the case, and well, think about it. It's not so trivial. Okay, the second remark to make things clear. These two pictures, these two embeddings, they represent the same graph. Okay, so it's obvious that the graph structure is the same, but the embeddings, you cannot continuously deform this one into this one. Okay, is it clear? For example, you can imagine, well, okay, you are on the two-dimensional sphere, so you can try to push the loop this way to come back on the other side, but you would end up with something like this. You can never deform this one to obtain this one. Well, this can be easily seen. For example, this face here has degree 1, 2, 3, 4, 5, 6, and here you have no face with such a degree. Okay? So we have a clear distinction between planar graphs and embeddings of these graphs, which we call map. Okay, so okay, maybe before we start the exercise on the Corey-Vauquelin-Schaeffer bijection, I propose you to prove the well-known Euler formula that states that with a planar connected graphs, connected is very important, then the number of vertices plus the number of faces minus the number of edges is always equal to 2. Okay? So try to prove this. It's very classical, I know, but for those who have never seen this, might be useful. So maybe a little push. The idea is to argue by induction on the number of edges. Okay, so let's go. So we are, as I said, by induction. The case where you have only one edge, well, I leave it to you. And now, imagine that you have a graph, planar, so an embedding such that the edges, they don't cross except at their endpoints, and pick one edge, say this one. And since you want to do an induction, let's see what happens if we remove this edge. So we have two cases. First case, we remove this edge, and we still have a connected graph. Still connected. Okay, so if it is the case, then we can apply the Euler formula with the number of edges minus 1. So we get that in this new graph, well, let's say the number of vertices plus the number of faces minus the number of edges is equal to 2 in this new graph by induction. But it's easy to see that, okay, the number of vertices of my original graph is the same number as in this graph. Well, the number of edges, we just removed one edge. But the number of faces, you have to think a little bit. Here, you had a face here. And by removing this edge, this face and this one in my original graph, they have been merged in this one. So we must actually add one face to this graph to recover the number of faces of this graph. Is it clear? Okay? So we can easily check that the Euler formula holds in this case. Okay, the other case, you remove this edge, but you end with two components. These two components, they were linked by this edge that we removed. Okay, so we, as before, apply the Euler formula in each of the components. So in this graph, the number of vertices plus faces minus edges is equal to 2. In this graph, the same. So we just have to see what is the relation, what are the relations between the number of vertices, faces, and edges in these graphs and this one. So it's easy to see that the number of vertices in my original graph is just the sum. Okay, the number of edges, easy also. Just sum and add the edges, the edge that you removed. Okay, but for the faces, then there is, okay, what should we add? Okay, the faces of this graph and this one, but there is a little problem. Does anybody see what is the little problem? Yes. If you count the number of faces of this graph, you will count the external face once. And as well for this graph. So you count this face twice. So you have to remove one. Okay? So you deduce this. Okay? So the Euler formula is the first combinatorial formula that is useful when dealing with planar graphs. Okay, now we will move to the Corey-Vauquelin-Schaeffer bijection, which is, wonderful tool. If you remove the Corey-Vauquelin-Schaeffer bijection, basically the whole field of random planar maps well, scaling limit of random planar maps totally collapses. It's the, well, it sustains everything. So let's come back to this bijection. And, well, I give another example. So this bijection is between the set of planar rooted trees. You remember, you have an orientation. You have labels along the tree. These labels satisfy a certain condition, namely the variation of the labels along each edge is +1, -1, or 0. Okay, for example, here it's +1, here it's -1, and, well, I don't have any 0, but you can have 0 variation. And, okay, you want to associate to this label tree a planar map. So the first thing to do is to add an extra vertex with the label equal to the minimal label of your label tree, -1. And then you move in, this is the clockwise order. You do the contour of the tree. And, well, you are, if you are at this vertex, for example, you are looking for the first vertex with label that is 0, in this case, -1. And you will link this vertex to its successor. Okay, so let's do that. So this 0 must be linked to this -1. This 1 must be linked to this 0. This 0, -1. Okay, let's come to this -1, the only -2. Okay, there is only one -2, which is not on the tree, but this extra vertex. Okay, let's go on. This 0. Okay, I have a 0. I must find a -1, so I go till I find a -1 here. Okay, link them. Well, the choke is not good enough, but okay, this one 0. Okay, and 0, -1, -2, 0, -1 here. 1, 0, 0, -1, -1, the only -2. Well, see, I've drawn this edge in that direction. I should have done, with my convention, I should have done this. Always clockwise sense. But remember that we are on the sphere. Well, yeah. I mean, the Earth is a sphere. So you take this, go along to France, China, and then you go back with this door, and you have, well, you will have this. Okay? Thank you. Okay, so I can draw this edge this way. Then this 0, -1, and this -1, -2. And then I end with the first vertex I started from. Okay? Now I erase the tree, the dotted tree, and what I see in green is a planar map, a quadrangulation, whose vertex set is exactly the vertices, composed of the vertices of the tree, plus this extra vertex. And, well, maybe it's not so clear, but it's the same as this one. And furthermore, okay, so this map is not rooted yet, but remember that in the bijection, we need another extra variable in order to root the quadrangulation. And this quadrangulation is always rooted at the edge that we constructed from the root vertex of the tree, so namely this one, this edge, and the extra variable, the coin that we had in addition to this tree, is here to decide the sense the direction of my oriented edge. Okay? Clear so far? And I have a distinguished point that come from the extra vertex that I put on top of the tree. Okay? Yes?
You put this edge through the channel. Before putting this edge with -1 to
Okay, I can start at every vertex. I could have started here. It would have been exactly the same picture. Imagine. I started here. You agree? Imagine I started here. Okay, I want to link this 0 to the first -1 I encounter in the contour. Okay, this one. Then this -1 to the -2. Okay, this part is the same. Okay, then I arrive here. I put this one, then this 0 to the this 1 to the 0, and then I end here.
What was strange for me is the following: you put this edge before putting all edges. I mean, you moved one edge before putting all edges. Maybe if you put all edges.
Which one? Which one?
Impossible.
I don't understand. Which edge did I put?
From -1 above to -2.
This one?
Yes.
No. I started with this one.
No.
Well.
Here.
Where around the world?
Oh, well. This one.
Yes.
I could have put like this.
Yes, but should be after that you should put the last -1 to -2. How you will do it?
Look. I don't cross. No, it's wonderful. I can assure you that this bijection it works. Not only with this planar map, it works. It's a bijection. It's a theorem. You can try it many times. It won't fail. I promise. Otherwise, I quit my PhD. Well, I have nothing to do. Okay. So, the main, I insist, the main feature of this bijection is that it keeps track of the distances in the map. So to see this, imagine that we add the minimal label of the vertices here, -2, to every label. So this -2 becomes 0, this one becomes 3, 0 becomes 2, 1, 1, 2, 3, 2, and 1. Okay? So now, look. Take this vertex, for example. What is the graph distance between this vertex and the pointed vertex? 2. Okay, this one. This one. This one. Okay. So you understood that, well, this one is actually 4, but no, I'm kidding. So once you've added the minimal label to all the labels, then what you see is the graph distance towards the pointed vertex. That's pretty obvious from the construction. Namely, remember this one, you linked this 1, 1, I mean this vertex, to 0. Okay? So it's obvious that this one is at distance 1 from the 0. And remember, this 2 has been linked to this 1, 1. So it's obvious that this 2 is at distance, well, at most 2 from the root. But this 2 is only linked to a 1 or a 3 before him in the contour sense. So it's obvious from the construction that the labels you see are the graph distance in the map from the construction. Because, okay, you don't need the tree. You have 0, you have 1, you have 1, 2, 3, and I tell you the 1 is linked to a 0. Then the 2 is linked to a 1. Then the 1 is linked to a 0, and the 3 is linked to a 2. Well, it's obvious that the graph distance, they are the labels. It's the same in this construction. So this theorem is obvious from the construction. Okay? And, okay, now imagine 10 years ago, I come with a very big problem, and I tell you, well, I'm interested in random planar maps. Imagine, take a random quadrangulation with n faces, n very big. What is the typical distance between any 2 points in this quadrangulation? Well, the naive answer is in between 0 and n. But to say much more than that, it's rather impossible. It's very deep. Here, you know that since you have a coding by label trees, this distance between 2 points will be roughly given by the labels along the tree. And now you know by the Brownian snake, by the Jean-François Le Gall lectures, that it's, the rough order is n to 1/4. But it's not obvious at all. You could say, well, it's two-dimensional, so central limit in this direction, central limit in that direction, square root of n, n to 1/4. No, it's not obvious at all. Okay? Well, now we will try to understand the reverse construction of the Schaeffer bijection. So now I start with a map, and I want to construct a label tree that will give rise to this map. Okay? So the first thing to do is to give yourself a starting point, which will play the role of this guy. And now you know if, well, to discover this bijection, you don't find first this way and then this way. But now you know that these labels have to be the distances to this pointed vertex. So let's start. Well, I should label all the vertices of the map with respect to their distances to the root. 1, 2, 3, 4. And now I want to construct the tree. First things to do is to show that the map, the quadrangulation, is bipartite. So Gregory told you this morning that bipartiteness is equivalent to the existence of a bicoloration of the vertices in black and white, such that two neighboring vertices are in different colors. Okay? So that's the first question. I ask you, why a quadrangulation, or more generally, a map such that all the faces have even degree is bipartite?
Fill it up by going around the cycle, just alternate colors. Since they're all even length, you won't make a mistake.
Exactly. So you have to prove that all the cycles in your map are of even length. So bipartiteness, let's see, B property, is equivalent to the fact that if I take U and V, two neighboring vertices, then the graph distance between V, okay, let's call this one V star. The variation of the graph distance is always 1 in absolute value. So why will this imply the B property? Because then you take, so this tells you that two neighboring vertices, then the distance towards the root is even and odd for one guy. So you color in black, say, the odd guys, and in white, the even guys. So we have to show this. So take two neighboring vertices linked by an edge and try to connect them to the root vertices, to the root vertex, sorry, B star. And these two paths are geodesic paths. Okay? Geodesic path. Okay, so it's sufficient to show that the length of this, okay, they can merge. In this drawing, they merge. It's sufficient to show that the graph distance of u and v towards v star cannot be the same. Of course, the graph distance is, well, this inequality is obvious. This is not obvious. So we just have to show that they cannot be at the same graph distance from the root. Okay? So if it is the case, then take Is it still working? Okay. So now take two paths, and if they are at the same graph distance from the root, then this cycle that you see here has odd length. This cycle has odd length, okay? Because here you've got the same, since they are geodesic paths, they are, I'm doing like Vincent Beffard, they have the same length, so they merge, they have the same, you know, so you add one, so it's odd. So now you want to show that it's not even. To show this, you just count the half edges inside the cycle. So you count for the faces. Here, you've got faces. You count the number of edges, say half edges, inside each faces. So count half edges. So half edges, I mean oriented edges. So for each face, since you've got a quadrangulation, each face has 4 neighboring oriented edges. Clear? So let's say that you have f faces. So 4f is equal to, so the edges that are inside your cycle, they will be counted twice. Okay, imagine you've got an edge here. This edge is going to be counted with this face and with this face. So 2 times inside edges plus the edges on the boundary are counted only once, plus edges on the boundary. Well, then you see that the number of edges on the boundary has to be even. Okay? Clear? So every cycle in a quadrangulation has an even length. Okay? That means that you have this property. Okay? So now, what could a face look at? Well, a face is like this one. You go from, so I means for distance to the root equals to I plus 1. You could have I plus 2, then I plus 1. Or you could have something like this. I plus 1, I, and I plus 1. They are the 2 types of face. Okay? Clear? So now the ID, but, well, Gregory did the drawing this morning. Remember, well, no, I won't go into details. I just give you the rule. The rule is, so did I take the counterclockwise sense? No, clockwise sense. So you go around the face in clockwise sense. And if you are in this type of face, then you add a red edge like this in your drawing. And otherwise, if you are in this type, you add an edge like this. Okay, so try to do this procedure on this picture and see what happens. This is a very easy exercise. Everybody can do that. Otherwise, the Clay Institute will not fund you anymore. I've drawn the picture on the sheet, on the exercise sheet. So Philippe Di Francesco in kindergarten, he learns how to deal with orthogonal polynomials. I deal with this kind of thing in kindergarten. Good question. What do we need to prove? Nothing so far. I just ask you to do the drawing and to see what happens. What do I need to prove? I want to prove something. Relax. Not in exercise sessions. And at the end, he just adds the little square. Now the proof is done. Okay, correction. This face, you go in clockwise sense. This face is of this type. So you add an edge like this. Okay? This one is of this type. So you add an edge, well, like this. Okay? This one is of the second type. This one is of the first type. Okay, and now the tricky one, the external face. Scrooge, 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 Scrooge. Yes, we are on the sphere. You have an external face. So you go, well, I say in the clockwise sense. So in that sense. Okay, so I move like this, 0, 1, 2, 1. So I'm in the first case. So am I wrong? No. So 1, 2. So these two has to be linked to this one. Okay, see what I have. What do I have? I have a spanning tree. Well, almost. I have a spanning tree of the vertices of the map, except the pointed vertex. Okay? So first we have to prove this, that we always get a tree, which is not obvious. So to do this, it's sufficient to see that we don't create cycles. Why? So because of the Euler formula that I'm erasing, well, nice. But you all know the Euler formula. So I remind you that if you have n faces, you are a quadrangulation. Then automatically you have n plus 2 vertices. This easily comes from the Euler formula. Maybe I should do that. Okay, so if you want to do this properly, you count the number of faces. for each face, as I said on this blackboard, well, I mean on this part of the blackboard, if you count 4 times the number of faces, then you will count twice the number of edges. Because any edge is counted twice. Once with this face, once with this one. Well, you could say, no, take this one. Take this face. This edge is not counted twice. This edge only belongs to this face, not to 2 faces. But here the convention is to count this edge twice. It's the convention, so that everything works. So this is always true. So now you apply the Euler formula, and you get that the number of vertices plus faces minus edges equals to 2. So V minus N equals to 2. Because F is equal to N, and that's it. Okay, so you've got N plus 2 vertices. So remember that you wanted to prove that the orange tree is a spanning tree of the map minus this vertex. So this spanning tree must have N plus 1 vertices. Okay, so a spanning tree, a tree with N plus 1 vertices must have N edges. Well, yes? For F, because we have a quadrangulation. Every face has 4 adjacent edges. So this is the number of oriented edge or half edges. Okay? So I recap. If you want to prove that this orange thing is a spanning tree on the vertices you want, you just have to show that it has n edges and no cycle. Because if you know that you have n edges and no cycle, then you are a tree with n minus 1 vertices. Okay? And furthermore, it's obvious from the rule that you applied that the minimal vertex, I mean the vertex in a face whose graph distance to the root is minimal, is never an extremity of the orange edge that you had. Okay? So the 0 here is never an extremity of one orange edge. So I'm pretty sure, that the orange thing does not span this one. Okay? So you've got n plus 2 minus 1 vertices left. That is n minus 1. So if we prove that we don't have any cycle, we are done. Because we have n faces. N faces. In each faces you have an orange edge. So I recap n edges plus no cycle. This implies a tree with n plus 1 vertices. And the only vertices left are the vertices of the map minus this pointed vertex. Okay? So I let you think about that. Well, just to entertain yourself, imagine that you applied the Corey-Vauquelin-Schaeffer construction with this orange tree. Imagine, for example, that this tree was rooted here. Okay? So you want yes. It's okay, it's okay. I fear something, but okay, it's okay. So look at this orange tree, and now just imagine that you want to apply this construction. And for example, I don't know, start from this vertex. So what you have to do is to go in clockwise sense around the tree, like this, and to link every corner, every vertex, with its successor. Okay, so take this one, these two. What is the successor of these two? So we go around the tree till we find a 1. No 1, no 1, no 1, no 1, no 1. Puff! 1. So I have to link these two to this one. Oh, well, I already have an edge here. So let's move on. 3. We have to link these 3 to the first 2 that we encounter in the clockwise contour of the tree. Okay, clockwise contour, 2. Hop, an edge. Oh, there is already an edge in the map. 4. 3 is here. Oh. So we can check that it works. Now, imagine that this tree was not rooted at this 1, 1, but at these 2. It doesn't change anything. Okay? Just keep that in mind. Clear? I mean, I will erase and yes? There is no other, good question, but there is no other, okay, you know. But this leads me to another bijection that has been discovered maybe 3 years ago by Grégory Mirmont, which is the multi-pointed bijection, where you don't have only one source, but many sources, and then you have to wait for the end of the next week, and the last TA session will be about this multi-pointed bijection. Yes, they will. They will create, you will see, they will create a map with the number of faces, which is equal to the number of sources. And the number of sources. Okay, maybe to be even clearer, imagine that we start with this tree. It has to be clear like tap water or sparkling water if you want. If it's clearer, I don't know. Everybody has to understand the Schaeffer bijection. So imagine that we start with this tree. Say this tree is rooted, well, okay. I know that somebody will ask a question. Well, these labels, they are all positive. Okay, let's subtract. Well, imagine that this tree was rooted here. So if the tree is rooted here, there must be a 0 here. So let's subtract 2 to every vertex. Okay, now apply the Schaeffer construction with this tree rooted here. So what do we have to do? What do we have to do? No, what do we have to do? Thanks. What do we have to do first? Yeah, but I erase the quadrangulation. So First, add another vector. No, it's important. First, add another vertex whose label is the minus one, the minimal the minimal label -1. Sorry. So, for example, let us add this vertex. Where was it? Here.
Yes.
Well, -2. Now go around the tree and apply the Schaeffer construction. So this 0 has to be linked to the first -1. This one. Ah. Then this one has to be linked to the first 0. Where is he? Here. 0 to the first -1. Here. Then we go along the tree, and we find this -1, which has to be linked to the only -2. Then we go along the tree. 0 to the first -1 that we encounter. This one. 0 to the first -1. -1, 2, 0, -1, 0, -1, -1, 2. And we come back here, 0 to the first -1 here. And then 1 to the first 0 here. Then 2 to the first 1. And then the vertex we started from. Okay? Okay, so let's come back to the proof of the reverse construction. Okay, so imagine that during the process of adding orange edges, we created a cycle. We have a cycle of orange edges inside my big quadrangulation. Okay? So by planarity, I know that the pointed vertex here is not on the orange thing. So the pointed vertex must be either here or here. Say it's here. Okay? And now the trick is to consider along this orange cycle the minimal label and to find a contradiction.
Isn't it true? I mean, in this, when you are constructing the tree, there is like no double edge. All the edges are simple because you are going in reverse direction. No, for the tree. When you are constructing the tree from the.
Ah, you're doing a proof of that?
Yes, no. Yes, so I'm proving that. So suppose you have a graph with n edges and n plus 1 vertices, and all the edges are simple. Then it has to be a tree.
No, no. This is a graph with n minus 1, n, let's say n plus 1 vertices, n edges. And yeah, if you say connected, then you don't need a cycle. Okay? Well, so as I said, we can consider the minimal, a vertex along this cycle with minimal label. So I recall that the label is the distance towards the root. Okay, so since this I is the minimal label, then the next one can be either I plus 1 or I. Well, it cannot be I minus 1, right? And from the construction, the difference of the labels along every orange edge is either 0 or 1. Okay? So we are in this situation or in this one. Okay. Now, does anybody see a contradiction? Where? Okay, so let us take this case. It's easier. This case. So we've linked I to I. That means that we were in this case. Okay? So if we were in this case, then this face here must be of this kind. I minus 1, I minus 1. Okay? And now, what is the trick? The distance, right. Imagine that we go from this vertex, which is at distance I minus 1 from the root, so we can go towards the root. Okay, no problem. But from this one, we have to go to the root. So follow a geodesic path that goes to the root by a discrete Jordan theorem or whatever, something trivial. It has to cross this orange cycle. Okay, it crosses here, this orange cycle, with a label which is strictly, less than I minus 1. My gosh, this is not possible because this I was minimal along the cycle. So we consider a geodesic, discrete geodesic path that goes towards the root. This path crosses the orange thing. Okay? So try to do the second case. It's the same. Yeah, I know it's 6 o'clock, but motivation. Up. I'm a gym teacher. Allez! Well, the first one who take this chalk and can draw the picture, I offer him a caipirinha. Come, take the chalk. No, not you. No. Come on. Not you. No, another guy. Not a TA teacher. Well, you're the only guy who understands
okay,
my...
I might be able to do it.
but you don't drink alcohol.
I drink, I just don't drink beer.
Okay, I will do it. Okay, so we are in this situation. So we have a face here. Well, let's see. What's the sense? I plus 1, I plus 2. So that means that we were like this. We had a face like this. Okay? Sorry? Because of the orientation, yeah, of the... There will be an I plus 1 on top. Because if there is an I here, back to this case. Okay? If there is an I here, we are back to this case. So I'm saying that here you must have also an I plus 1 if you want to have something strange. Okay? So if there is I plus 1, I plus 1, that means that, whoops.
They are outside, okay. But suppose that there are two of them. The bottom is I, on the top
Okay, I here, I plus 1 here. Okay, just do that.
And imagine this one is either I, so we are in this case, or it must be I plus 1, so we are in that case.
Exactly the same. Okay, let's do it slowly. I have I plus 1. Okay? I plus 1. So I look at my picture. That means that, let's see, I have a face like this. I minus 1. Okay? Now, let's see what this vertex is. Cannot be I, otherwise I am in this situation, it's done. So it's I plus 1. And if it is I plus 1, I look at the picture, the face that I should have is like this. I minus 1, I. Okay? And I'm back to this argument by considering two geodesic paths that goes from this I minus 1 to the root and from this I minus 1 to the root. Isn't it beautiful? Yes, it is. Okay, so now we have a spanning tree of our map, but without the pointed vertex. So how should I first root my tree? Because I remind you that the bijection, maybe I should write it here. Here.
Let me ask this question. Why is connected?
Why is it connected? You have n edges. You have n plus 1 vertices. You don't have any cycle. You're a tree. You're a tree. You're a tree. You're a quadrangulation. You're the same. I should say you're a labeled tree. Okay? Well, it's okay if you want to prove this, use Euler formula. Because a tree is nothing but a map with one face. Okay? So the bijection was between the set of Qn. So let's write this to put the emphasis on the two things I add on top of my quadrangulation. I have a rooted edge, oriented edge, and a pointed vertex. Okay? And the bijection is between this set and the set of trees Tn with labels rooted plus a coin flip. Okay? So I told you, well, 15 minutes ago, 20, that once we've done all this successor thing, once we have added all the edges with the Schaeffer bijection, then in order to recover the pointed vertex and the root edge in the quadrangulation, you have two things to do. The pointed vertex in the quadrangulation is the vertex that you add. Okay? And the root edge is given by whatever. Here you've got a 0. So this 0 will be linked to some minus 1 somewhere. It could be even this guy. Okay? So this 0 is linked to some minus 1. This 0 is the root of the tree. Your tree in Tn is rooted. Okay? And this plus or minus 1 is here to give the orientation of this edge. Okay? So you recover the pointed vertex and the root edge. So can anybody with a caipirinha at the end tell me where I should root my orange tree so that I recover, say, this quadrangulation? Who thinks it's here? thinks it's here. Well, you're right. Nobody thinks anything. Maybe you can think something. No, it doesn't depend on the epsilon. Okay, try to think a little bit. Had I rooted my tree here, so I apply this, I know that the root edge must be the edge that comes from this minus 1. Okay, so this minus 1 has to be linked to a minus 2, which is this one. So whatever the epsilon, it's all about this edge. If this epsilon is that, then that. Well, it's not the edge I wanted. So who thinks it's this one? Thank you. So it's this one. Why? Because you have, if you choose this one as the root of your tree, you know that the root edge of your map has to be the edge that comes from this 0. So this 0 has to be linked to 1 minus 1, which is this one. Okay? And now it's all about this edge. And now I just decide the orientation of my edge according to the coin flip. Okay, so let us do it again. I want to root my quadrangulation here. Which guy should I choose? This one or this one? Who votes for this one? That's a bit better. Yes, it's this one. Okay? So you see that if I reroute my tree, I just change the root edge of my map. Okay? So the routing of the tree corresponds to the routing of the map. Now, let's try something more strange. New exercise, nothing to prove, but take the same map, the very same map, and change the pointed vertex. Okay? You decide now, okay, the exercise is I want the map such that the root edge is here and the pointed vertex is here. Okay. Maybe we need the second exercise sheet. Come on. Let's interact.
So where?
I won't come to your next tutorials, but
Very interested. So where did you say we rooted this?
so we want to route the map here and to point the map here. And I want to know what is the tree, the labeled tree, that I should consider such that this tree is associated to this map. Okay, pointed here.
Yeah.
So all the distances will be about distance to this vertex. Okay, so let's go. One is missing. Yes?
Oh, yeah, obviously.
Okay. Now, what should I do? What should he do? He should go, and you should designate the next victim.
I should designate the next victim. How? What a
No. So, no. Go. I want everybody to come to my next tutorial, so it's just a joke. Don't be afraid. It's finished. just for my birthday. Thank you for the present. I enjoyed it. So now I just apply this construction. So let's do it. I'm missing some orange chalk. So let us do with brown. Sorry?
You want it back?
Okay, so here I'm type 1 face. Here I'm type 1. 1. 1. 1. 1. And this one is type 1 as well. So what is the tree that I have? Is this orange tree. Well, it's still a tree, right? And if I want my map to be rooted, let's say, here, I should root my tree. No, no, sorry, here. I'm just trying to, yes, here. I want my map rooted here. So I should consider this one as the root vertex of my tree. So my tree must be something like this. Was it the tree that I considered at the beginning? Okay, so you see something strange, but very important for the following, is that when you change the root edge, well, it's just rerouting the tree, but when you change the pointed vertex, the vertex from which you measure the distances, then, well, practically everything is destroyed. Look at this tree. It's not the same at all as the preceding one. Okay? Is the Schaeffer-Corey-Vauquelin-Schaeffer-Bajgeschen clear? Clear, clear, clear? Please ask. It's the time. Okay. You're asking a question. Maybe it could be useful for the others. So what's the question?
I didn't get what the plus minus 1 does.
The plus minus 1 does. So the plus minus 1 is just here to decide the orientation of the edge.
But does it give the same thing? If I don't change anything yet, does it give the same element?
Well, oh, you see, I root my tree here. So I know that the root edge is the edge coming out of this one, which is this edge. Now I want a rooted, oriented edge. So I just have to decide one orientation. That's exactly what the plus minus 1 does. So let's say plus 1, you always go from I to I minus 1. Minus 1, you always go to I plus 1. So here, I go, if I have plus 1, say, so I go from I to I minus 1. So I to I minus 1 in this direction. So this epsilon is just here to give the orientation of the edge. Please, I assure you, I give a caipirinha to everybody who asks not a silly question, but almost silly. Please ask.
Does the root of a tree has always to be connected to V star?
Does the root of the tree has always to be connected to V star? Never. Never. Okay, caipirinha, but never. Why? Because the 0 is V star, exactly. But the tree, the orange thing, never, never, never spans V star.
No. Okay, but the root of the tree connects by a select dash with that.
No. Take this example. Not always, no, but I will give you an example. take this tree. Start with 0. Here, you've got a -1. Here, you've got -2. OK, let us apply the Schaeffer biject to this tree, and let's say that we have a coin flip +1. OK, so what do we have to do? We add -3 here. And now we apply the Schaeffer construction. So this 0 has to be linked to a -1. Oh, this one. Well, what's the color? OK, in green. This -1 to the -2. This -2 to the -3. This -1 to the -2. And this 0, it's OK. Here is the map. And as you see, the root of the tree here is not linked to the pointed vertex, which is here. And the orientation, I have been given +1, so I look +1, I go from I to I -1, I to I -1 in this direction. OK? One caipirinha. Another? Alors, this is not a piece of cake. Not, well, half a piece of cake. But as you can see, it's almost obvious. Almost obvious on the drawing. Yes? Yes, it was a question. It's a second caipirinha. This is not a question. Well, was it a question? No. It wasn't. The question is it clear that this construction is the inverse construction of this one? OK. Which direction you think is the easier one? The easier one is to, well, let's see, to show that once you've constructed a map from a tree, then you apply this, you recover the tree. This is easier. But another point, another interesting point. As you can see from this construction, the edges of the labeled tree, they correspond to the faces of the map. So the vertices, they are the same up to this extra vertex. The faces, they correspond to the edges. And the graph distance correspond to the labels. OK? Okay. So the only thing that you have to prove is that this map is either surjective or injective. Because, well, you know that they have the same cardinality. Well, this is a bit cheating, because you know that they have the same cardinality because of Tut. But if you want to prove that this is, if you want to reprove Tut's result, that's not the thing you're going to do. You're going to show that this is a well-defined bijection. But for you, once you know, it's easier. So you choose the side you prefer. Yes?
How do you decide from the...
So you see, I should offer a caipirinha at each question, but now I'm ruined.
From the root of the tree, if you have several corners.
Good question, very good question, because I was not very precise at this point. I was expecting this question. So I'm sorry, I'm going a little bit over time, but I will give you caipirinhas for everybody. So if you have several, something like this. Really? You didn't hear the question? So if you have several children, if the root of your tree has several children, how do you decide what is going to be the root edge of your map? So this question is, well, a root tree is not only a root vertex. You are given a corner of this vertex. I mean, this tree is not the same as this one. It's a plane tree, exactly. So when you root a plane tree, you are given a vertex plus a corner of this vertex. So to decide what edge is going to be the root edge of your map, You just decide that it's going to be the edge that is coming from this corner. If it's a 0, this goes to a -1, and it will be this one.
The first one.
Not the first one, the one that comes from the corner that where you rooted the tree. Good question. Yes?
From the same level tree, if you use the maximal +1 and do the same proceeding corresponding to the distance of to the maximal value +1.
To the maximal value +1, I don't understand.
No, you use the minimum of the weight -1. So if you use the maximum +1 and do the same proceeding corresponding, do you get the same map or it's a continuation of this map?
I think I don't understand what you mean. You want to apply the construction, but not with the labels given by the distance to this root.
To the maximal. And
What is the maximal? What is the maximal? Maximal what?
If it's the weight, the maximum weight is 3, you add with 4, and when you're searching for the next one, you search for +1, not -1.
Well, it's the same question. You just do that. I think either I don't understand or it's maybe I don't understand. You want to, okay, if I understand well, then you have a tree here, and instead of searching for +1, for -1, you are connecting this one to this 2.
Yeah.
Well, I guess you do exactly, so I can, okay, take this tree, 0, -1, 1, 2, and 2. This tree, you just reverse all the increments of the labels along each edge. Here it was an increment of 1, so you change into an increment of -1.
The same is doing -2.
Exactly. So it's just a convention if you.
Whether you add V star, the minimum weight
Yeah,
-1 or the
exactly.
Now the root is -1. The old method is
No, maybe we talk later. But this won't have the good property of the distance. The labels won't represent the distance anymore. And you want to keep track of the distance. Any other question? Okay, thank you. So,
in this case, you add the root with star, it's the -1. What
no.